Hello, this is Dr. Liu. In this video, I have two questions to discuss as examples of conservation of momentum in collisions. So let's look at the left side. And this question comes from University Physics, published by OpenStax, chapter number 9, question number 35. So train cars are coupled together by being bumped into one another. Suppose two loaded train cars are moving towards one another. The first having a mass 1.50 times 10 to the fifth kilograms, that's 150,000 kilograms, and a velocity of 0.30 meters per second, that's relatively slow. And the second having a mass of 1.10 times 10 to the fifth kilograms and a velocity of minus 0.12 meters per second. So according to this diagram, the positive velocities are pointing to the right, as we usually do that, and the negative velocities are pointing to the left. And the question is, what is their final velocity? So when they bump into each other, they combine, they'll be moving at the same speed. And since we know this left one has slightly more mass than the right one, we know that, and also a higher speed, so we can anticipate the two train cars will move to the right with a very low speed. So now let's look at conservation of momentum as a system of two objects. So this one, we'll call that number 1 with mass 1. So m1, which is equal to 1.50 times 10 to the fifth power. Right, and here's v1 given, m2, 1.1 times 10 to the fifth power, and velocity is given. So we have two masses, and they each have initial velocities. So for momentum conservation of momentum, so say that before equals after. So initial equals final, and initial will include both masses because they're both moving, they both have momentum. Final will include the combined mass, which moves at a single speed. So over here we can say the initial is m1 v1 plus m2 v2, and the final, they combined, right? They are coupled together, so they're moving at the same speed. Let's put a v final here. They coupled, right? So coupled, it means v1's final equals v2's final, and we may as well just define a single final velocity, right? Let's get rid of that. One final. Okay, so we combine the masses because they're moving at the same speed. All right, so let's plug in the numbers. 1.50 times 10 to the fifth times velocity is 0.30 plus 1.10 times 10 to the fifth times the velocity is minus 0.12. So that is equal to the sum, which is 1.50 plus 1.10. So I'm adding these two together because they have the same order of power of 10 to the fifth, right? So that's our combined mass times final velocity. Okay, so let's use our calculator to do this part. Let's call up Python, move it to the side. Okay, so 1.5 times this 10 to the fifth power, so 10 raised to the power of 5 times 0.3, and there's a negative 1.1 times 10 to the fifth power times 0.12. So this is the left side. Now we should have a very large number because their masses are huge. So 3.18 times 10 to the fourth power, if you count the decimal places, move that 4 times to move it to the right of 3. So it's 3.18 times 10 to the fourth power. Manage that. So left side is 3.18 times 10 to the fourth power. This is a momentum unit, so the unit is Newton second if you Still remember from previous videos, Newton second. And the right side is 2.6. This is easier. 2.6 times 10 to the fifth power V final. Alright, so now V final is equal to 3.18 times 10 to the fourth power. Cricket. Grab a ruler. Over 2.60 times 10 to the fifth power. So here's what I would do. I would divide these two and try to do the order of magnitude in my head. But since I have a calculator, I could skip that part. But I'd like to do this: 3.18 divided by 26.0. So what I had was this is times 10 to the fourth power. This is also times 10 to the fourth power. I took 110 and just multiplied that through with the 26, right? So I basically made a common power of 10 so I can divide them out easily. These are gone, so I'm just 3.18 over 26. This makes it easier to enter into the calculator, and you'll likely make less mistakes with less numbers. So we have 0.122. Let's manage that. 0.122 meters per second. And this is positive, so it's directed to the right. Can't really draw too straight today. So that's direction to the right. Okay, so this question is not very long. The reason that I show this question is because I want to establish something as a common theme, how to solve a problem with momentum conservation. So we have before momentum equals after momentum, and both before and after contains two objects, or even could be multiple objects. It's less likely to be multiple objects because they have to collide somehow, like a three-party collision at the same time. You said that's not very common. So we have two objects. Their individual momentum is calculated and added together. And we need to be careful with the velocity directions because they do differ. And then the final momentum would be the m1 times v1 final, m2 times v2 final, except that they're combined, they're coupled. So we're saving one unknown, right? So they have the same exact final velocity, and that is the variable we're solving. So this momentum conservation provides you a single equation because conservation means before equals after. That is one equation, right? So that's how you solve it. Look at the system and enumerate all its momentum terms at one point in time, and try to do the same thing at another point in time, the initial and the final. Okay. Okay, so now let's move on to the right side. This is University of Physics, published by OpenStax again, Chapter 9, question number 37. So in this figure, we have a bullet and a block of wood. Okay, so let's take a look. We have a bullet of 200 grams traveling horizontally towards the east, so this direction, with speed 400 meters per second, which strikes a block of mass 1.5 kilograms that is initially at rest on a frictionless table. Okay, so here are the question parts. After striking the block, the bullet is embedded in the block, and the bullet move together as one unit. So this is very similar to the two train cars, except that their masses are very different from each other. 200-gram bullet is very, very rare. I've read about bullets and their speeds. The 400 meters per second is pretty common, but 200 grams. Typical bullets are only in grams. So this is a very high-speed, heavy projectile. In reality, it would probably destroy the block, but that's for the calculation's sake. Let's say the block is not destroyed. All right. So there's a series of questions here. What is the magnitude and the direction of velocity of a block bullet combination immediately after the impact? This is the same as the left side, the train cars coupling into each other, right? So then what about the rest of the questions? So what is the magnitude and direction of the impulse by the bullet on the by the block on the bullet? So we can calculate that. I think we know how to do impulse. What is the magnitude and direction of the impulse from the bullet on the block? Okay. And then if it took 3 milliseconds for the bullet to change its speed from 400 to the final speed after impact, what is the average force between the block and the bullet during this time? Okay, so it's a combination between collision and some momentum and impact impulse calculations. So now let's review what we did from the left side. We used conservation of momentum. We had before and after momentum. This one's even easier. The block was sitting at rest, so there's no momentum on the block. All right, so let's start doing this. Initial equals final, and we'll save some space over here. How about we give it some symbols? This is M, because it's a bullet and block, right? Bullet, M, block. I would probably call it M wood and M bullet, but let's just respect the questions. Whoever wrote it. So the M bullet, velocity bullet, plus M block times 0 at rest. Right, so that's beginning. And the final is they're stuck together, so they're moving together. So bullet plus block with their final velocity unknown. So that's the same way we were doing the left side. So let's plug in the numbers on the left side. So the bullet is 0.200, so 200 grams in kilograms, and the speed is 400. That's equal to, add them together, so 1.5, 2.2 plus 1.5, so 1.7 kilogram. Or we can say here, move that decimal place 2 times, move this 2 times, so 20 times to 4, right, it's 80. So 80 equals 1.7 V final, so we can easily solve V final, which is 80 over 1.7, and let's call up our calculator. Now we can move it to the left side. So 80 over 1.7, that gives us 47.1. So okay, so just as I discussed, the values are pretty unrealistic. Something moving at almost 50 meters per second, that's very fast. It's over 100 miles per hour. So if this thing doesn't get destroyed or even chip some materials off, that would be really unrealistic. So let's just use our imaginary duct tape together. So this thing just actually still moves in one piece. So we're done with the first part. The second part, magnitude and direction of impulse by the block on the bullet. Okay, so let's recall the change of momentum of anything is due to the impulse. So impulse on the object, which is the impulse is force and duration. So force and duration. Right, so that's whole thing. The change of momentum, let's say change of momentum of the bullet should be momentum final minus momentum initial. This is all about the bullet, since I said that already. So this will be the final so mass of the bullet, V final, minus mass of the bullet, and then V initial. This is just V bullet, right? So that's that, and that's the change of momentum. Okay, so let's calculate this change of momentum, which is impulse. So the bullet's mass can be factored out. So final minus the initial bullet, right? So that's the change of bullet momentum. Let's say that change of bullet momentum is impulse by block, which is equal to this quantity here. So let's plug in the mass of bullet, which is 200 grams. And then the final velocity is 47.1. The initial velocity is 400. So as you can see, this is a negative, which makes sense. The impulse on the bullet is negative. That takes momentum away from the bullet, so the bullet slows down during that impact against the block. Okay, so let's use our calculator. So 47.1 times minus 400, so that's a change of velocity. So that value times 0.2, so we have a negative 70.6 of impulse. And this impulse has a unit of Newton seconds. So this is the impulse on the bullet by the block. And the next question is the magnitude. Okay, direction. Sorry, direction is to the left because it's negative, right? So the next question is the magnitude and direction of impulse from bullet to the block. So that should be change of momentum of the block, which is the impulse by the bullet. So that will concern the block's final minus block's initial momentum. So if I just follow the bullet's version, so the block's mass, final velocity minus initial velocity of the block was 0. So the block has 1.5 kilograms of mass, then multiply by 47.1. Okay, so 1.5 times 47.1. So we get the basically the same result. Let's just round to even, so we have 70.6. So we have 70.6 newtons second. This is to the right because of positive. So as we can see, the two numerical values are the same, which means what happens is the bullet transfers some momentum to the block, and the block basically takes the same amount of momentum. So the bullet would increase the momentum of the block by this amount, and the block will decrease the bullet's momentum by the same amount. So there's an equal exchange, which indicates the momentum conservation. Okay, so the last one here, if this exchange took 3 milliseconds, and what is the average force between the two? So we can use either one of them, say the increase of the block, say this here. So that is equal to this quantity of 70.6. And according to the unit, it's Newton times second. So if I divide this by the time, the 3 milliseconds, I should get Newton, the force. Right, so let's still do the formality. The force between the two times the duration. So the force is the change of momentum of the block over the duration of, and that allowed the change. So 70.6 over 3 milliseconds, so 0.0003. Let's use our calculator. So 70.6 over 0.0003. So we have a pretty large average force. So this is in the hundreds of thousands, so 235,000 newtons. So an average force, very large. Under this force, I can't imagine the block will still stay in the same in one piece. But that's up to our imaginary theoretical duct tape to hold it together. So we're done with both questions, and the summary here is you want to use this momentum conservation before and after. So you will enumerate what is the momentum before one or two objects, what is the momentum after. And in this collision that we can call this inelastic, completely inelastic collision, the two masses are combined, so their final velocities are the same. Let's imagine they are not. For example, if this lock fails and they just bounce off each other, then they won't be moving at the same speed after the collision. And also, if the block was not very thick, the bullet penetrates through it, then it would still be moving faster than the block moves, so it wouldn't be the same exact final speed. And then we'll have to use two terms for the final momentum, one for each because they don't share speeds anymore. Thank you.